Hi everyone, so it's Ian here, and I'm just going to do a brief video explaining how the set of code works for importing and working with the city temperatures dataset that you're going to be using for the hack activity. You can go through this in a self-directed way. You don't have to follow this video if you're comfortable with the code. It is relatively self-explanatory, but it's just included here for a video in case you need me to explain anything. You'll notice if you look up in this data file, this 3C hack day 1 basics of Python, it is an extension of the basics of Python code. So where we did the cars and imported the array, and we used the Hubble dataset as well. Okay, so that's all included above in there, and you can run all of that. And I'd suggest running all of that block by block, or just coming straight down to this data manipulation with pandas, where we got the city temperature dataset mentioned. And if you hit runtime, you can run everything before that. And that means it's already imported all of the libraries and the tools and the things, a bit like, as I said yesterday, with getting all of the tools out of the garage ready to do the job that we're actually trying to do, like fixing the hole in the wall. Whereas here, instead of fixing a hole in the wall, we're looking at city temperatures, and that's what you're going to be doing in your groups with your own research question. So first things first, we need to upload our data set. So click the files and then click the upload, and then tell it to upload the city temperatures data set. I've already done this, but you'll notice when you do it, there'll be the name of the file and a circle down here because it's a relatively large data set. It is bigger than Excel can open in one go, but that's showing you why we need to be working with programming and with Python and with pandas in particular. So first things first, we're going to read in the dataset, and that's going to take a moment to do, but it won't take too long. See, Excel couldn't even handle it, so impressive that it's managed to do it that quickly in 3 seconds. Let's have a look at what the top of the data is, just to see what's going on there. So it's got regions, it's got countries. If there are states in that country, it'll list those, but there isn't many states in other countries outside the US generally. There are cities there, so, and then the month, the day, and the year. So January the 1st, 1995, and then the average temperature is listed there as 64 degrees. And it won't take long for you to realise that these are not degrees centigrade, hopefully. It's actually degrees Fahrenheit. But let's describe the data and see what's going on then. So there are 2.9 million entries for month and day and year, so almost 3 million dead sets. We can see all this information here, but ultimately it's a bit meaningless. The E plus 00 means like times 10 to the power of whatever the 00 or that number is. So here it's a 03. So the year, the 25th percentile value of that, or 25% of the way through the data set, is 2000. So it's 2 times 10 to the power of 3. Okay, let's have a look if there's any non-values in there. In state, there's lots of non-values. We expected that because we've got not a number or non-values here for this first country, so that's, and city, so that's likely there's going to be the non-values in there. But fortunately, there's no non-values in the region or country, city, month, day, year, average temperature. So we can work with all the rest of those things. We just need to get rid of state. We'll do that later though. Let's see what the regions are in the data frame. So in the regions, we've got Africa, Asia, Australia, South Pacific, Europe, Middle East, North Africa. So it's pretty much done by continent, but not quite. There's some slightly more fine grain in certain areas. So as I mentioned, we've got the data in Fahrenheit, but I struggle to work with Fahrenheit, so we need to work with Celsius instead. So we've got a little function here that takes a row of data and then converts it to Celsius from Fahrenheit. So all we then need to do is apply that function to the data table or the data frame that we've got. So we're going to apply it to the average temperature column of our table and just apply the to Celsius function. So when we run that through and then we look at the head of the data, again, we'll see that instead of being in Fahrenheit, now everything's in Celsius, and it's much easier, at least from an English point of view, to work with, given what we're used to in the temperatures. So we can get a summary of what's going on by grouping the subcategories together so we don't have to deal with lots of different column headings and structures there. So if we just group it by all of these different features and look at the average temperatures, then we can see the average month value, average day value, and average temperature. Average month and day aren't particularly meaningful, we don't need to see those, but we can see the average temperature for each year then. And we've got some strange values here and some big variations. So for Puerto Rico, we've got an average temperature in 1995 of 27, and then in 1996 an average temperature of minus 15, and then of 15 degrees in 1997, and then of 11 in 1998. So really, really variable. In fact, unbelievably variable. And this is where we need to make sure we're using our heads and thinking about the values and the information that we're being shown. Now, I'm going to focus on Vienna, and we're going to get digging down deep into the data for Vienna and seeing what's going on to try and understand why there might be such big variability in Puerto Rico and some of the fine-grained details of the data set. So let's get the data where the city is called Vienna, and you could choose any city name. So we're going to copy that into a new table called Vienna so that we leave the old data set and frame it without modifying it, but just have Vienna. And then we're going to group everything by year and drop the month and the day columns and look at what's going on. So we can look at just the average temperature for each year for Vienna. And we'll see it's 10 degrees, then 8.7, 9.8, 9.8, and 10.3. So always, whenever you're looking at any summary statistics, think, does this match up with the narrative and the story that you're expecting from the data? And if it does, great. Then you're using your intuition and it seems to make sense. If it doesn't quite match it with what you're expecting, then you need to work out why. So let's look at a plot to see what's really going on. If we plot the average temperature for Vienna and see what's going on, we can also do a polynomial fit, just a straight line fit like we did in the introduction to Python session with an A and a B, or an M and a B I've used here just to show you that you can use different variable names. And we can see that there's a generally increasing temperature over time with a steady curve, which, you know, matches with most of what science is telling us, except for a big drop in 2020, which seems a bit odd. So let's try and look at what's going on in Vienna in 2020. So what I'm going to do is take some slices of the data set next. We'll look at the tail first of all and see the average temperature did indeed drop to 7 from 11. So that's a bit odd. So if we look at the data, or the time series as it's called, because it depends on time, and see what's going on with the trend in the data. So here we're taking slices and we're going to add, specifically just get the values for 2020, 2019 and 2018. And then we're going to plot for each of those slices, we're going to be plotting the average temperature, and this will show us what's going on over time, but with different colors. Okay, so you can change the city round in this code. I'm not expecting you to understand all of what this code's doing, but I am expecting you to be able to change the city name to whatever city you're focusing on or research question you're focusing on, to be able to mess around with that and understand what's going on. Don't worry if you break it, just re-upload, start again, or try and fix it with your group. So we've got 2018 here, 2019 here, and 2020. So far less data for 2020, hence the lower expected temperature, because it's not got summer data. So that seems to make sense. We've only got so much data in 2020 till when the dataset was finished and able to be downloaded, and that's what I've worked from. But we've got more data for 2018 and 19. What we can also notice though is that we've got some really low values in there. So we need to go through and see if the data needs cleaning and processing. So let's get the number of null values. Well, there's none, that's great. Number of not a value. There's none, that's perfect. But there are some really low values. We're focusing particularly on the year 2018. So we've got 3 really low values that are less than -20, and we use -20 as just a proxy for it's really cold, and maybe it gets really cold in Vienna, but you know, -20 was a good cutoff to say if it's below this value, then it's really low. So let's look at those 3 values in more detail. So we get the index of those 3 values where it's less than -20. So ignore the typo there, it is less than -20 in the actual code. So these are the index values in our dataset. So row 641,048 and 641,362 and 641,363. So again, far easier than Excel. We've just found our specific values that are where it's less than a specific -20. So let's see what the actual values are in those locations. So when we print it out, the value of our data frame we're using called sliced, where it was a data slice. Remember, we're working with the 2018 data. So we've got the 4th of January, we've got a value of -72.8, 14th of November and 15th of November. Bit odd that they've all got the same temperature value, right? Well, if you look back on the Fahrenheit value of this, it's actually a -99. They'd put it in as an error code, i.e. we don't know what the average temperature was. It was either corrupted or not recorded for that day, or something went wrong. So we need to clean those. And we can do one of two things. We can cut the value from the data frame, or we can impute it, so fill it in based upon what we know is happening around then and from the data, and with some logic. I'm going to do both of those things here just to show you, so you can choose which or either one you want to work with when you're actually doing your own data set. So the first thing we're going to do is just remove this first one, 641,048. So let's just drop it from the data set. Drop. So that's gone. If we rerun this line of code, which you can do by hitting play again, that would be a different value, a normal temperature value now. But I'll leave that to you to do. Now, let's look at the next pair. So we've got two values of -72.8 surrounded by actual good data. Where it was 7, it was 9 degrees, something happened here, and then it was 2, and then it was -1.5. So first of all, let's take the the mean value of the data either side of this -72. So let's take this 9.3 and take this 2.8, add them together, divide by 2, that will give you the mean or the average temperature between those two, and then we'll put that value in there. So at row 641,362, so this first one, we're going to say it's half of the value just before that and the value after. So fill that in. Now, if we look at it again, we see we've got a value of 6.05, which kind of makes sense. We've gone from 7 to 9, then down to 6, then it'll be something along the way, probably between that and 2.8. Okay, nice and simple. So we've just imputed and filled in some missing data. We've got one final row to do though. So we've got another value of -72.8 that needs to be dealt with. So we're just going to find the median of all the values in the run up to this, and then say that that median value is the value that it should be on that day, which is a fairly good proxy as far as meteorology is concerned when you don't have a lot of background, prior knowledge of what's going on. So we reckon then actually it's going to be 9.3, which may seem a little high, but it happens on day to day. You can get big fluctuations in temperature. It's not a big surprise. So now we've dropped those from the data set and we've imputed the other two values, we can actually see what's going on in more detail with the data for 2018 for Vienna. So if we look into the statistics and replot it, we've lost our big drop values that we had on the earlier plot, and it's a much clearer trend that we can see what's going on. So we've got a maximum value of 27 and a minimum value of -10 on one day. That just sort of came out of nowhere. So with understanding what's going on with the data, we've got a minimum and a maximum value. We could do other things like find the average through the standard deviation, the mean. We could look at the highest temperature in summer. We could fit a polynomial curve to this and then see what the shape of that curve is. Is it increasing really quickly over time or changing on average? You can answer whatever research question you want with this. And all I'm expecting you to do is to just work through the data, choose a research question as a group, and try and test out the tools, techniques, and things that we've done. And finally put it onto 5 PowerPoint slides. You don't need to present it, but on 5 PowerPoint slides, explain what your research question was, what you tried to do to the data, did it work, show some plots and some results out there, and then identify any limitations or what you'd like to do if you knew more about AI and had more time. Good luck, and I'm looking forward to seeing the results of it on Friday.